Okay, so here is section 3.5, and this section is titled Numerical Descriptions of Data. So what we did in the last couple sections was look at visual descriptions. We were looking at graphs and charts and things like that for qualitative and quantitative data. And what we're going to look at in this section is numerical descriptions, which is going to be probably a more important tool that we're going to be using going forward. Um, so first, to give you kind of an overview of how this is going to pan out, when we talk about numerical descriptions of data, what we want to do is sort of encompass what a data set looks like, and there's a few different aspects of a data set that we want to address. Okay, um, so um, if I think about the graph of a data set, right, and maybe I just draw like a quick histogram or something like that. Okay. Um, one of the ways that we can describe what the data set, contains or looks like is to say, well, on what number is, the data set centered. Okay, so we have different ways of measuring where the center of the data set is. Okay, and then we also have measures for how spread out it is, right? So does it stretch out very far to either side? Okay, are most of the data values sort of clumped in the middle? Okay, so we'll have numerical ways to describe the spread, okay, of the data. Or sometimes that's called the variation. Okay, and then we'll look at things like how do we describe an outlier, which we talked about briefly, but we'll have a way for measuring whether or not something is an outlier. Okay, so let's start by talking about measures of the center of the data. And the good news is this is going to be something that a lot of you have probably already seen some of, okay, or maybe all of what we're about to describe, okay. But let me just give you kind of a quick reason for why do we have more than one way of measuring the center, okay. What's going to happen is in different situations there's going to be a different way. Different ways of measuring the center are going to be better in some way, or more appropriate to a data set. Okay, and there are more ways of measuring the center than just these. What we're going to do is just go through a few of them, and we'll give reasons why each one is useful in some particular context. Okay. All right. So the three measures of center that we're going to talk about are going to be the mean, median, and mode. Um, so let's start by talking about the mode. Okay. So first we'll give a definition for what the mode is, and we'll look at some examples. So the mode is the data value that occurs most frequently. Okay. So if I wanted to find it, I'm just going to look at how often each data value occurs. This is the one with the highest frequency. So if we have a frequency distribution, the mode is the data value with the largest frequency. Okay. So that's pretty simple to find. One of the things to keep in mind when we're looking at the mode is that it's not the frequency that is the mode, it is the data value. Okay, and we'll highlight that when we go through an example. Let's just get a definition for each one of these out here, and then we'll look at examples. And what we'll do is we'll have a data set, and we'll find all three measures of center. Okay, so we'll sort of do all the examples at once. The median is like the middle data value. So this is the data value in the middle of a sorted list of data. Okay, To find it, what we want to do is put the data in an order, typically in numerical order. Okay. And then determine which one is exactly in the middle. Okay. That really only works with numerical data, right? I can't uh, numerically order qualitative data. And then we have the mean. This is the average of the numbers. Okay. This is sometimes, if we want to be really mathy, right? If you want to learn new words, this is the arithmetic average. There's a different way of averaging numbers. Well, there's a lot of ways of averaging numbers. But there's another, way, a geometric average of numbers or geometric mean that we're not going to talk about in this class. But this is what most people think of when they think of average. Okay. Okay. So all three of these could really be considered an average, but when people say find the average or this is the average, usually it's referring to what we use as the mean. Okay. So to find this, we add up all the data values and divide by how many there are. Okay, we'll go through an example of that too. When we're going through, notes and formulas and things like that in the future, because the mean is so commonly used, because we're going to, we'll use it frequently in this class, and because it's used frequently in formulas for other things, we have a symbol for it. Okay, and we actually have more than one symbol for it, because when we're looking at data sets in statistics, often we want to talk about a population, and then sometimes we have a sample from that population. And we can find the mean for both, and those might be different numbers, so we have different symbols to keep things nice and clear. Okay. So for the mean, we'll have the symbol mu, right? So it's a Greek letter. Oh, actually, I think, let's just scroll down. So here's our Greek symbol mu is the population mean, and x bar is the sample mean. Okay. Now, what I want to explain really quickly is what we have over here to the right of the equals, because that looks like a bunch of craziness, right, when you first look at it. Okay. So when this says mu equals, and then it has all of these symbols over here, okay, this symbol here is the capital Greek letter sigma, and it stands for sum. So when we're writing mathematical formulas, this just means add up everything that follows. Okay, so this whole thing, sigma x, means add up all the x's. And if x's are my data values, it means add up all the data values. Okay, when we're talking about data sets, we use n to denote how many things there are, right? N for number of things. We use a capital N for the number of things in the population, right? The size of the population. We use little n for the size of the things in the sample. Okay, so if I add up all of the things in the population and divide by how many things there are in the population, I get the mean of the population. If I add up all of the things in the sample and divide by how many things there are in the sample, I get the mean or the average for the sample. Okay. Let's look at some examples of computing mean, median, and mode here. So, once again, something to keep in mind when we do examples like this in class, we're always going to work with a really small data set because we want to be able to manage things. When we're talking about like summarizing data, these numerical descriptions of data, we want to talk about tools that'll be useful for bigger data sets. Okay, so in this table, I have weights of cats in pounds, and if I just have 5 numbers, okay, we don't really need things like the average to look at 5 numbers and sort of understand what's going on. Okay, we're just using small examples because that's helpful. If I have a big data set, it's cumbersome to work with. So for learning what's going on, we use these small data sets. But we want to, the whole point is for bigger data sets. All right. So before we get into finding the mean, median, and mode, okay, what we're given is a table of data where we have the weight of cats in pounds, and we want to sort of circle back to our beginning definitions here and identify what is the individual, what's the variable, and what type of variable are we working with. Okay, so in this case, my individual is going to be just some, a cat, right? So it says, suppose a vet wants to find the average weight of cats. The weight in pounds of 5 cats are in this table, so an individual object is going to just be some cat, right? A cat or a randomly selected cat. Okay. The variable is the piece of information that we have written down. Okay, so when we write down 6.8, what we're writing down is the weight of the cat. So the variable is the weight. Okay, and this is a numerical or quantitative variable. Okay, so now let's look at how to compute the mean, and I'm going to show you how to do this a couple of different ways. So first, let's look at the actual, computing this using the actual formula. Because this is the weight of just 5 cats and not all cats, this is going to be a sample. So I want to write the symbol for sample mean. And then I want to add up all of the cat's weight. So I'm going to take 6.8 plus 8.2 plus 7.5 plus 9.4 plus 8.2. And I divide by how many I have. Okay, and there's 5 of them here, so I'm going to divide by 5. When I add up these numbers, okay, bust out a calculator and add these up, I get 40.1. And when I divide, I get 8.02. We should always have units here when we're working with a numerical variable. Okay, so the way to interpret what this number is I could say, like, the cats weigh 8.02 pounds on average. Okay, I'm going to come back and show you how to compute this on your calculator. Let's talk about the median next. Okay, so in order to compute the median, what I want to do is rewrite my list in numerical order. Okay, so if I go back up to my sample, right, I can see, all right, the smallest number is 6.8, then 7.5, then I have a couple of 8.2s, and then a 9.4. Okay, so I'm gonna rewrite that that sorted list. So we had 6.8, 7.5, 8.2, another 8.2, and then a 9.4. Okay, and I can see, all right, out of these five, in the dead center, this middle value is the median. Okay, so that means that the median is equal to 8.2 pounds. We still have units on the median. Okay, so if I interpret that, I could just say, well, the middle weight of the cats was 8.2 pounds. Okay. The mode is probably easier to find when I have a sorted list also. It's not necessary, but it makes things a lot easier. But if I have a sorted list and it's small like this, I can find the mode and I don't really need to create a frequency distribution. I can look at this and say, oh, 8.2 occurs twice. Nothing else occurs twice. Okay, so so 8.2 is the mode. Okay, so then to interpret that, and I already have that typed in, the weight that occurred the most for the cats was 8.2 pounds. I can't draw straight. Okay. Um, it's possible for a data set to have more than one mode if there's a tie, right? So in this case, 8.2 occurred twice and nothing else did. But if I had two 8.2s and two 7.5s, then I would have two modes. And we call it bimodal. Okay. If nothing occurs more than once, then there's no mode. You can't have everything tie for one. That's not helpful. Um, if I have a bigger data set, that's when it could be difficult to just visually inspect and see which one occurs most often, and that's when something like a frequency distribution might be more useful for finding the mode. Okay. All right. And again, what I want you to notice here is that the mode, 8.2 occurred twice. 2 is not the mode, though. The mode is the data value. So it's 8.2 that is the mode. Okay. Or we should say 8.2 pounds. All right. Before I show you how to compute this stuff on your calculator, I want to really quickly kind of circle back to the median. Um, here, when I had 5 data values, um, or any odd number of data values, we have one that's definitely in the middle. But if I have an even number of data values, let's say that there was, a sixth one, I wouldn't have just one number that's in the middle. I would have you could think of it like two middle numbers. Okay. So we need to have a rule for how to find the median when we have an even number. Okay. So let's look at a different set of data. Okay. And all we've done is we've added one number to our list of 5. And we want to find the median for that one. Okay. And, once again, we should always start by identifying what's the object, right? Cat. What's the variable weight? What type of variable is that? Okay, we have numerical or quantitative. Okay, so then what we're going to do is we're going to create a sorted list. Okay, and here kind of have that typed in already, so I'm not going to handwrite it. What we do is we say, well, if I have an even number of things, then in my sorted list, I'm going to have a middle two numbers instead of just one middle number. What we're going to do is just average the numbers, right? We're going to find the mean of those middle two numbers. Okay, so here, the median is going to be 7.5 plus 8.2 divided by 2. Because I'm averaging the two numbers, I'm adding up these two and dividing by 2. Okay. So when I compute that out, I'm going to get 7.85 pounds. Okay. So the middle weight of this set of cats is 7.85 pounds. All right. What I want to do now is show you how can you use your calculator, and I'm going to show you using a TI calculator. If you have a different type of calculator, you should have a way of doing this also, but I'm going to show you on the TI. It's the same on the TI 83 and 84, but we're going to go through how would we compute mean and median. Your calculator doesn't compute the mode for you, but usually that's not very challenging to find. Okay, so here's my calculator, and what I want to do is first I need to tell it what the data set is. Okay, so I think in an earlier section I sort of gave you some rough idea for how to compute stuff on your calculator. Here we have it written out very explicitly. Okay, so first we're going to push the stat button. That brings up this menu, and the first thing on here is edit. Right, so I'm just going to hit enter or press the number 1. And that brings up this list editor, and that's what I need to do to put in the data. Okay. So I'm going to hit stat and then hit 1 or just hit enter, and I'm going to enter my data into L1. And we could really use any list. It doesn't have to be L1, but we're just going to use L1 for this example. Okay, so here we have our data set again. Okay. So I'm just going to enter these data values in, right? So I have 6.8, and I hit enter, and it shows up, right? Okay, so we'll enter all of the data in. Okay, so this was my list of 6 data values. Okay. All right. Now the good news is, if I want to compute numbers from this data set, I have like one thing that I'm going to press, and it's going to compute everything for me. And then I just pick out whichever one I need in that particular situation. So my calculator will just compute them all at once and show them to me. Okay. So we did this first step. We entered our data into L1. Next, what we're going to do is we're going to press the stat button again, but this time we're going to go over to a different menu, right? So I'm going to hit the stat button again, and instead of the edit menu, I'm going to press over to get to the calculate menu. And again, I'm going to use the first thing on here. So we can press the number 1 or just hit enter to enter in this one variable statistics. Okay. Now, depending on your calculator, it might look different than this. And I'll show you the other way to look here in a second. So you could get this menu style where it says, okay, here's your list, L1, that's where we entered things. Frequency list, well, I don't really have that right now, so I'm just going to leave that blank. So we can just hit calculate. Okay. The other way that this could look is when I hit stat calculate and I hit one variable statistics, it might just pop one variable statistics up on my screen. And then if I want to tell it, oh, I want to do these statistics on the data I put in L1, I want to tell it my list L1. And I can see L1 is in blue above the number 1. So if I hit my blue second button and hit 1, it'll put L1 on there, and then I just hit enter. Okay. So either method you use should bring you to this screen where it says one variable statistics, and it gives you a list of stuff that you have to scroll down to see all of because there's so much. Okay. So here's a picture of putting the data in. Okay. Then we have the one variable stats, right? Here's our little menu. And then this is what we get. And we have kind of two, screenshots here to show you all of the stuff. Remember that our symbol for mean was X bar. So that's where we find the mean. Okay. So if it says X bar is 7.73, okay, then I can write that, and that I know is the mean of the sample. Okay. Median doesn't have a symbol, so I just look for MED for median. Calculator doesn't write out the whole word, but I think we can figure out, oh, okay, that means median. Okay, so that's the 8.85 pounds. And that 8.85 is what we computed when we did it by hand. Okay, so after putting the data values into the table, so let me back up again. Oops, that's the wrong button. So I hit stat, edit, I put all the data values in the table. So you hit the stat button again, and then we go over to the calculate menu, and that's where we get that one variable statistics. Okay. All right. Maybe really quickly, just to give you a sense for what's going on, let me mention what all of these different things are that it tells you, okay? Just so there's not like a bunch of mystery behind what's going on. So the X bar, we already talked about, that's the symbol for the mean or the average, okay? So obviously that's going to be our average, okay? Then we have this sigma x, and we talked about that a little bit when we had the formula for mean, and we said that means add up all of the x values. Okay, so if I just wanted to add up all of those cat weights and say what's the total weight of those 6 cats, that's what it is. This is the weights added up. We're not going to use this directly in the class. Okay, so this would be helpful for picking apart formulas a little bit more, but this isn't something that we're going to use. Okay. The same thing with this next one, this sigma x squared is saying square all of the x values and then add them up. Now, one of the things that we will do at some point, I might give you a data set, and I might tell you what is the sigma x squared of the data set. And the reason that I do that is when you go to compute stuff, if your number matches, you probably entered all the data correctly. And if it doesn't match, then you definitely made a mistake in entering the data into your calculator. Okay, and so that's just kind of a way to double check and make sure, was there an issue with how we entered things, or is there an issue with how we're computing things? Okay, so that's something that you might see again. We're not really using that to compute anything. We're just using it to make sure that we entered all of our numbers in correctly. Okay, these next two we're going to talk about in more detail later. The Sx and the sigma x are going to both be numbers for standard deviation. Okay, and when we go over standard deviation in detail, then we'll talk about why they're two different numbers. One of them is a formula for the sample, and one of them is a formula for the population, and they use slightly different formulas, so we get a different number. Okay, then we have n. That's just how many things are in my data set, right? The number of things, and we had 6. Then we have the min value, that's the smallest value in the data set. Right, on the flip side of that, the max x is the biggest value in the data set. Okay, dead center is the mean, and then Q1 and Q3 are quartiles, and again, we're going to talk about those later. Okay, so almost everything on here is something that we're going to either use or talk about we'll never use this sigma x, but we've kind of already seen it. And this sigma x squared is only going to be used to make sure that there wasn't a typo putting stuff in our calculator. All right. So what I want to do next is sort of give us a reason why we have mean, median, and mode. Why do we have three different things for measuring the center of a data set? So what I want to do is show you this example. Okay, and this example is going to show you what effect does an extreme value have. Okay, so what we're going to do is we're going to take the data set that we just entered. Okay, so I'm going to go back here and hit stat edit, and you'll see the same data set, 6.8. Oh, sorry, we're going to change the data set. We're going to 7.5, 8.2, 8.2, 9.4. Okay, so this is our original data set of 5 data values, and then we're going to enter in one extreme data value, one value that looks like an outlier, right? That's very different from the others. Okay, so let's look at this data value 22.1. So I'm going to enter that in, and if I think of cats, right, it's a big cat. It's not an unrealistic cat, it's just a very big cat compared to the other ones. Okay, so maybe just as a reminder, let's look at the 5 that we had from before. Okay, so I'm just gonna write that over to the side. All right, with just the 5. Okay, and these are from our first example. Okay, so I go to the one variable statistics, I hit calculate, and we had that average of 8.02 that we computed by hand. And then we have our median of, it was 8.2, but we'll go down and look at it, right? The median is 8.2. Okay, and we should always write the units on here. All right, now what I want to do is, I'm just going to use this for reference really quickly. Okay, now let's look at this data set that we have of 5 plus the 1 extreme value. Okay, so I'm gonna go back to my calculator, edit the list, and throw in that big cat that weighs 22.1 pounds. Yeah. Okay, now let's compute the mean and median for that. So I go to calculate, one variable statistics. Now my mean is 10.37 if I round. The median is still 8.2. Okay. So X bar is 10.37 pounds. Okay, and the median is 8.02 pounds, or sorry, not 0.2, 8.2 pounds. Okay, and I can sort of see that because these are written in order. So I can see, oh, I have these middle two values. Since they're the same, when I average them, I'll just get 8.2. So we could do that by hand, or we could do that on our calculator. Okay. All right. So one of the things that I want you to see is when we throw in this one heavy cat, the mean jumps up by over 2 pounds, and in this case, the median doesn't move at all. No change at all. Okay. So, here the mean jumped up a bunch. It became higher than the median. The median didn't change when I added in that one extra value. Okay. Okay. So the mean jumps up, but the median does not. And, one of the things that we need to keep in mind is that the mean takes into account every single data value. When I look at the formula, you add up all of the data values, right? They're all sort of given equal, importance. And so if you throw in one extreme value, that's going to impact the mean by a lot. Okay. If you want to think of like a more extreme case, let's suppose that I took our Math 101 class and I looked at everyone's annual income, right? And we just had all of those out there and we averaged them. And then let's suppose that we had, say Jeff Bezos join our class, right? The CEO of Amazon, right? And we look at his annual income and he makes, I don't know, it's hundreds of millions or maybe billions of dollars a year, something like that. Okay. That would throw the average income up by an astounding amount, right? With that one extra person. Okay. If I look at the median income, if I line everybody up and look at the middle value, when you add one person, it doesn't really matter, if that's the biggest value. It doesn't matter if it's the biggest by, you know, just barely, right? If that value was a 9.5, or if it was a 10 zillion, right? It's just the next one on the right. So if I were to look at the median for these 5 data points, it's this value. If I add in one bigger value, it's now averaging these two, right? So the median doesn't change by very much, right? When I add in a bigger value, in a way, I'm accounting for that because it's another bigger value, so it does shift what the median is. But the numbers in the middle don't change. So the shift isn't going to be by very much. Okay. So when we look at a data set and we include some extreme value, okay, that extreme value is going to impact the mean by a lot. It's not going to impact the median by very much. Okay. So um, an extreme value has a large impact on the mean, small impact on the median. Okay. So if we want to talk about what is the middle of the data set, right? Remember, our whole point of this discussion was to look at measures of center. If I look at 10.37 pounds, right, if you just look at these 6 numbers, that's bigger than all but one of the data values, okay? So it's probably not giving me a very good measure for what the middle is, right? When I'm talking about 6 cats, and I say the average weight is 10.37 pounds, well, only one of the cats weighs more than 10.37. The other 5 cats are all less than that. So that's not really giving me a good sense for what most of the cats uh, are like. Okay, so it's not really a very accurate measure of middle anymore, or the center of the data set. When I say 8.2 pounds, that's right in the middle of what all the cats weigh, so that's probably still a good measure of the center. So when we have an extreme value, the median is going to be a better measure for what the center of the data set is. Okay. Okay. So this is the reason why we have more than one way of measuring what the center of the data set is. Okay. Um, because depending on the data set, right, you know, our normal way, right, of the mean of measuring the middle of a data set might not be very good, right? The median is much better when we have an extreme value. Okay. if you read news articles or listen to like the news or something like that, and you hear people talk about income, right? When we're saying like, what's happened to the annual income since, the COVID epidemic or something like that. Okay. Anytime you hear reports about income, they don't talk about the average income. They'll always talk about the median income, right? Again, because income is one of those things where you have extreme values, right? You have people like, Jeff Bezos that make billions of dollars that are in our population, okay? And that's not really, if I talk about average and there's a big move in the average, it might mean that, some of these really rich people are suddenly making a lot more money or making a lot less money. And that's not really giving you a good sense for what's going on in the whole, economy, what's happening to people in general. Okay. Whereas if I look at the median, that gives me the middle value, and that's often a better way to track what's going on with, the whole population. Okay. So for things like income, where you have extreme values all the time, um, median is better. And so you'll actually, hear that reported. Okay. All right. I want to talk about one last type of averaging, something called a weighted average. Okay. Um, so weighted averages are used in things like your grades, right? If I look at the syllabus, okay, it says exams are this much percentage of your grade and homework are this much percentage of your grade. Okay. So you don't just take a homework and an exam and average them together to find your grade, right? We would have to figure out, you know, what's the appropriate rate. Well, what percent of your grade does that count for? Okay. Um, so if I'm going to go into too much detail in this example yet, let's talk about what this weighted average looks like. How would I compute it? Okay, so we're going to look at an example of computing a grade in a biology class. Okay. So in your biology class, your final grade is based on, and we're just going to give this as an example, a lab score, two major tests, and a final exam. Okay. And each one of these are graded as 100 points. But the lab score is worth 15% of the course. The exams are worth 25% each, and the final exam is 35% of your grade. Okay. So each of your scores is out of 100, but not all of those 100 points count the same. Okay. So let's look at your weighted average for the course. Now, what we're doing is we're building up good habits here. We're going to start by identifying what is an individual, what's a variable, and what type of variable it is. Okay. Um, so the individual that we're collecting data from is going to be a biology student. Okay. The variable, the thing that we're trying to, the piece of information that we're going to be looking at um, is your grade in the class. Okay, and what type of variable is that? Well, that's numerical or quantitative. Okay, so what I want to do is show you how to compute this, but we're not going to do this by hand, right? We did those examples of mean and median, and we did the first couple examples by hand because it's sort of easy to write down. Um, but like, going forward, it's a lot easier to compute mean and median if you just type them into your calculator, right? Well, weighted average is going to be similar. That's a lot easier to compute if we just type it into our calculator. So that's what we're going to do. Okay. So what we're going to do is, we'll sort of, the notes sort of detail this. What we want to do is enter the data in. So I'm gonna go through showing you entering the data in my calculator. So when I hit stat and I hit edit, the first thing you notice is that I still have old data from a previous example. So there's a few different ways to get rid of this. One way is just to hit delete over and over again until I've cleared everything out. Okay. Another way, let me just enter some things back in here for you. Another way, if I had like a lot of stuff entered in, and I don't want to hit delete 10 times over again. Okay. When I'm in my data set, I have a bunch of stuff and I don't want to hit delete over and over again. What I can do is I can hit the up arrow so that I'm selecting the whole list at once. So then if I hit enter, it allows me to edit the list all at once. And the thing that I want to do is get rid of everything. So I can clear all of that information and then hit enter. So that's a quick way to wipe out everything in your list all at once. Okay, I'm going to show you one more thing really quickly. Now that I've showed you how to clear all the list at one time, what I notice happens often to students is you'll go up here, but instead of hitting enter and then clear and enter again, you go up here and hit delete. And now L1 is gone. And you're like, oh, shoot, now what do? All my examples, I'm supposed to have L1. Now my calculator doesn't even have L1 anymore. Okay. If that ever happens to you, you can hit stat. And if you hit this setup editor, okay, instead of hitting edit and going into that list editor, if you go down here to setup editor and just hit enter, okay, it fixes it for you. Right now when I go to stat edit, L1 is back. Okay, and then I can say, all right, now be more careful and not get rid of it. Okay, so let's start fresh now. I want to enter the data into my calculator, right? So let's suppose my scores are 95 on the labs, 83 and 76 on the exams, and 84 on the final. Okay, we're going to enter that data into L1. That's the data that we have to work with. So we have that 95, then we have an 83 and a 76, and then on the final exam there's an 84. Okay. Now what we're going to do is we're going to go over and we're going to put the percentages over in L2. So the labs were worth 15% of your grade. So I put in 15%. I'm going to enter it as a decimal though, so 0.15. Okay. The exams were worth 25% each. So I put in 0.25 next to each of the exams. Okay. And then the final was 35% of the grade. So I'm going to put 0.35 next to that final exam grade. Now, the way that we computed average before is we hit that stat button, and we went over to calculate, and we hit one variable statistics. We're going to do that exact same thing again, okay? Except, and this is, listed here, okay? Except now, under frequency list, we want to include those percentages that we put in, okay? So that's going to be my, you think of as relative frequencies. That's why it says frequency. Okay, but that's where I want to put that information in. So I need to tell it, oh, I put that stuff in L2. So I need to hit my second button and hit number 2 so that it enters L2 on here. Okay, and now I hit calculate. And it'll compute X bar as the mean, and it'll compute the median. Right? Okay. So I wanted to find my average. I don't need the median here. That's not really a helpful thing. We'll talk about that. You can compute. Well, we might talk about that later, but right now the only thing that we were interested in was what was our weighted average. So I can see, okay, that's 83.4. So our weighted average is 83.4%. I say, yay. Okay. So that's how we compute with weighted averages. Okay. All right, now let's talk about outliers a little bit. An outlier, as we mentioned before, that's a data value that's really different from the other data values. So it might be very high, right? Like we had with the cats, that 22-pound cat was a lot heavier than our other cats. We could also have an outlier that's really low, okay, that's fine too. That's also an outlier as long as it's just very different from the other values. Okay. In the next section, we'll look at how to specifically identify if something is an outlier. Okay, so the 22.1 pound cat, you can look at that and say, like, I think we would probably all agree, yeah, that's very different than the other cats. That's an outlier. What if I said a 15-pound cat? Then maybe we'd be split. Maybe some people would say, yeah, I think that's an outlier, and other people say, well, I don't know if that's far enough away. And you can always find something, some data value in there where people start to disagree. Like, well, what about, a 13-pound cat? Is that an outlier? Well, it's definitely more than the other cats. Is it a lot more, right? How do I tell how much is enough to be an outlier? So that's what we're going to get into in the next section. We don't want to make this a judgment call. We want to have a set rule. This is the boundary. This is the number that marks, okay, this is when we have an outlier. So we'll look at that so that we don't have to, use our own judgment and intuition, which might be different than somebody else's. Okay. When we talked about the mean and the median, the difference between the two was that one of them, the mean, looked at all the data values. And so if you put an outlier or an extreme data value in there, the mean is impacted a lot by that. The median is not. So we're going to give a word to statistics or measurements that are not impacted by extreme values, okay? And so we call those resistant, okay? All right, so the mean is not a resistant measure, okay, because it is affected by extreme values, okay? The median and the mode are resistant measures because they're not affected by those extreme values, okay? So when we have a data set that contains extreme values, we want to gravitate towards using resistant measures to talk about the data. Okay? And if we have data sets that don't include these extreme values, then we typically want to use, from looking at measures at the middle, then we want to use things like the mean because it does incorporate all the data values. It's you can think of it in some senses as being a little bit more precise than say the median. And so if there's no problems with it, then we want to gravitate towards the mean. Okay. So a little chart here. So resistant, the median and mode, not resistant is the mean. When we talk about measures of spread, we'll expand on this list, right? We'll put the measures of spread that are resistant and not resistant, okay? And it's going to be easy to do because when I look at measures of spread, there will be one that is sort of based on the median, that's the quartiles, okay? Since it's built on the median, it'll also be resistant. We'll have another measure of spread that's built on the mean, that's the standard deviation. Since the mean's not resistant, if we build something on that, that's not going to be resistant either. So the standard deviation is also not going to be resistant. Okay. All right. So resistant versus non-resistant, that's why we have the median versus the mean. I didn't really give you a great reason for the mode. Why do we include it? The main reason that we want to have the mode in here, or maybe one important reason, is when I work with non-numerical data, the mode is the only thing that we can look at, right? I can't take an average of, let's suppose my data was your, favorite colors. I can't take an average of colors in a meaningful way. Okay? And we can't even really talk about the middle value because we don't have like one set way to list non-numerical data. Okay, so for example, if I'm asking people what their favorite color is, okay, and I want to write down that data, I could write down the data in the order that people told me, or I could write it down in alphabetical order, or I could write it down in the order that appears, say, on like the rainbow, okay? But like there's not one set way to order the data, and since the way that I order it determines what the median is, the median is not really a useful thing. It doesn't seem like it's very well defined. Okay, so the mode is going to be key when we have non-numeric data. Okay, and we also use it as a way of sort of establishing, okay, from this middle value, what's going on. Okay, so we'll talk about it with numerical data too. That's kind of like a rough idea for this most frequent thing. Okay. Um, but as we talked about, anything where we have extreme values and salary is an important one. Then we should be conscious of okay, if there's extreme values, the mean is probably not the best way to measure it. Okay, that's probably not the best way to summarize all of the data points. Okay, because it doesn't really give you a good sense of what the middle or what the center of the data is, right? Like we had with those weights of cats. Okay, uh, the mean was a number that's bigger than all but one of them. Okay, so that's not really giving you a good sense of what the middle is, right? If it's if it's bigger than almost all of the data points. The median is, though, right, going to be a nice middle value. Okay. Um, so that's why, um, when we have extreme data values, we want to use the median. Why do we use the mean, though? Why wouldn't we just always use the median? Okay. Um, the median is really good at dealing with those extreme values, but when I don't have extreme values, the mean does something nicer. And it's a little bit more subtle, it's a little bit harder to see, but let's suppose I have a big data set. Okay. Suppose I want to take, the average weights of all cats. And I just go down to different veterinary clinics or something like that and say, all right, weigh all your cats in your clinic. And I look at all these different veterinary clinics as different samples. Okay. If I take the median of each veterinary clinic and I look at the mean of each veterinary clinic, the means are going to be um, a little bit more consistent than, say, the median or the mode. Okay. And so when I'm using that sample as a way to measure the population, that mean is going to be a better tool because of that extra consistency. Okay. So again, it's a little bit more subtle, but if I don't have problems, the mean is going to work better. Okay. It's going to be a little bit more reliable as long as I don't have extreme values. Okay. So as long as we don't have extreme values, then the sample mean is a more reliable measure of the center than the median or the mode. Okay. Let's look at, I think my graphs fell onto the next page here. Let's look at we talked about shapes of distributions last week, and let's look at these different shapes and where the mean, median, and mode would fall on a skewed left, a skewed right, and a bell-shaped distribution. Okay, so I'm going to start with the bell-shaped distribution here, and with the bell-shaped, my tallest value is the mode, right? Because that's the most frequently occurring, but it's also in the dead center, so it's the median. And because this is a symmetric distribution, I have just as much stuff on the left and the right, and that'll give me the mean also. It's a little bit harder to look at and see what a mean is in a visual data set. Let me give you another way to think of the mean. And you're not going to be tested on this, but maybe this just helps you understand another connection. If I look at a set of data values, okay, imagine I have a number line. Okay, and I put some data values on that number line. So let's suppose I have the number 1, and let's suppose I have, a 3 and a 3.5, and I have a 7. Okay, if I imagine these data values as being like weights on a bar, the mean, the average, will be the balancing point. Okay, that'll be like, where I would put a fulcrum and it would balance exactly. Okay, so if I average 1 and 3 and 3.5 and 7 together, I get 3.625. Okay, so that gives me the balancing point. Okay, so if I have a symmetric data set, I can see, oh yeah, it's going to balance right here in this dead center, so I know that's the mean, right? So mean, median, and mode on a symmetric bell-shaped data set are all the same value. But now let's suppose that we throw in some extra data values and it's skewed left. So the mode is still this tallest point, but I have more data values to the left than I do to the right. Okay? That's going to pull the median over, but only by a small amount because, again, if I think of my ordered data set, instead of, that one middle value, now I'm moving left by a few values, okay? But it's the same numbers that I'm looking at. So the median is only going to go over by a little bit. But if I'm throwing in these extra points that are very small, then I'm averaging in these small numbers, and that's going to pull the average by a lot, right? That's what we saw with those extreme values. The mean is going to go over by a lot. The median is only going to go over by a small amount. Okay. We have the same situation, but just reversed when we skewed right. If I throw in larger data values, right, bigger numbers, then the mean is going to increase by a lot, like we had with the cats, right? The one big cat weight moved my mean over by a lot, and it'll move my median over by a much smaller amount, right? And that small data set, it ended up not moving the median over at all because I had those two middle values that were the same. Okay. So this is sort of a way to get sort of a visual idea with what happens to the mean, median, and mode with the inclusion of different extreme values. Or another way to think about it is just if I have a skewed data set, what's going on with that? And when I look at a bell-shaped distribution, it's like, oh, it doesn't matter which measure I choose, so we're just going to use the mean because it has that better consistency among different samples. But if my data set is skewed, even if it doesn't include an extreme value, if it's just skewed, I can see, well, a mean over here is probably not a very good measure of what the middle is. Okay, the median or the mode are going to give me a better sense for what the middle is, right, in a skewed data set. So whether we have outliers or we have a skewed data set, we should probably look at the median instead of the mean. Okay, so this just kind of gives us a little summary of what's going on here, right? When we have skewed data set or we have extreme values, then we want to use the median as a measure of center. And if not, then we should just use the mean. All right, that's it for today. Stop recording.